The Mollier chart is a plot of the specific enthalpy of steam against its specific entropy. The following figure shows a simplified, small-scale version of the Mollier chart. The chart displays many different useful relationships between enthalpy, entropy, temperature, pressure, and dryness fraction. It may appear to be quite complicated due to the number of lines, but it isn't rocket science. The Mollier chart includes constant enthalpy lines which are horizontal, since the enthalpy is plotted on the y-axis. Constant entropy lines which are vertical, since entropy is on the x-axis. The steam saturation curve across the center of the chart. This curve divides the chart into a superheated steam region and a wet steam region. At any point above the saturation curve, the steam is superheated, and at any point below the saturation curve, the steam is wet. The saturation curve itself represents the condition of dry saturated steam at various pressures. Constant pressure lines in both regions, constant temperature lines in the superheat region, and lastly, constant dry fraction lines in the wet region. A perfect expansion, for example within a steam turbine, as highlighted here, is a constant entropy process and can be represented on the chart by moving vertically downwards from a point representing the initial condition, in this example point A, to a point representing the final condition, point B in our example. A perfect throttling process, for example across a pressure-reducing valve, as highlighted here, is a constant enthalpy process. Recall, this was discussed in a previous video, and it can be represented on the chart by moving horizontally from left to right, from a point representing the initial condition, in this example point C, to a point representing the final condition, point D. Both these processes involve a reduction in pressure, but the difference lies in the way in which this is achieved. In the constant entropy process, so the turbine, the pressure is reduced from 100 bars down to 0.5 bar. In the constant enthalpy process, where a pressure-reducing valve is used, the pressure is reduced from 20 bars to 1 bar. These two examples illustrate the advantage of using the chart to analyze steam processes. They provide a pictorial representation of such processes. However, recall, steam processes can also be numerically represented by the values provided in the superheated steam tables. Typical examples were provided in the previous videos. This example is for the study of steam expansion through a turbine using the Mollier chart. Let's take a closer look. Let's consider the perfect expansion of steam through a turbine. Initially, the pressure is 50 bar absolute. The temperature is 300 degrees Celsius, and the final pressure is 0.04. As the process is a perfect expansion, the entropy remains constant. The final condition in terms of temperature, enthalpy, and dryness fraction can then be found using the Mollier chart by dropping vertically downwards from the initial condition to the 0.04 bar constant pressure line, as highlighted here. As seen here, at the initial condition, the entropy is approximately 6.25 kilojoule per kilogram per degree Celsius. When we follow this line vertically downwards until 0.04 bar is reached, the final condition of the steam can be evaluated. At this point, the specific enthalpy is 1890 kilojoule per kilogram, and the dryness fraction is 0.72. Okay, now remember, the final condition can also be determined by using the superheated steam tables. Let's take a closer look. At the initial condition, so 50 bar absolute and 300 degrees Celsius, the superheated steam has the following properties. For dry saturated steam at 0.04 bar, the same properties are as follows. Now, since the entropy of dry saturated steam at 0.04 bar is greater than the entropy of the superheated steam at 50 bar absolute, it follows that some of the dry saturated steam must have condensed to maintain the constant entropy. As the entropy remains constant, at the final condition, the entropy of saturated water plus the entropy of evaporation times the dryness fraction must equal the entropy of superheated steam of 6.25 kilojoule per kilogram per degree Celsius. Substituting for S sub F and S sub Fg, the dryness fraction can then be calculated. The same principle applies to enthalpy. The final enthalpy equals the enthalpy of saturated water plus the dryness fraction times the enthalpy of evaporation. Shown now on screen the properties of steam at turbine outlet, so point B, obtained from Mollier chart and from the steam tables for the sake of comparison. As seen here, the answers from the steam tables correspond closely with the results obtained using the Mollier chart. The small difference in value between the two sets of results is to be expected, considering the inaccuracies involved in reading off a chart such as the Mollier chart.